Hi, everyone. Welcome to Astronomy 236. This is week 13, and this is our last week of class. So, in this last week, instead of talking about the history of matter in the universe, we're going to dive into the future of matter in the universe. And in this lecture bite, we're going to start out close to home and talk about the future of Earth's atmosphere. So, it should be fairly obvious to you that the Earth is warmed because it's heated by the sun. If you go outside on a sunny day, you can feel the sun's warmth on your skin. And perhaps it's a little bit less obvious that because the Earth is warmed by the sun, it will emit its own radiation through the blackbody process. Now, remember, warm objects emit radiation that is given this characteristic shape. The hotter the object is, the brighter it will be, and also the bluer the light that it emits will be. So these are some curves for the blackbody radiation from relatively hot objects. Temperature is typical for stars, and you can see that they're emitting most of their light in the visible range here. And as you go cooler and cooler, more and more of the light gets emitted in the infrared range. Because Earth is warm, therefore, it emits its own blackbody light. And it turns out that the amount of light that Earth receives from the sun must equal the amount that it emits, or it would keep heating up and therefore emit more and more light, and eventually it would balance itself out. So, this is a little bit of a tricky concept to understand. So, I want you to take a look at this image here and think about it like this fountain. So, in each of these buckets, water is being poured in and all water is pouring out at the same time. And we can know that on average, the amount of water entering this bucket has to be equal to the amount of water leaving this bucket. Because if it wasn't, if more water was entering this bucket than was leaving it, eventually the level of water in this bucket would rise and rise and rise until it would spill out. But because we don't see that happening, we know that in fact, the amount of water entering this bucket has to be the amount of water leaving this bucket. If it were the other way around, if less water were entering than leaving, eventually the bucket would run dry. So we know that it has to be in balance, in equilibrium, as we say. And we can do the same thing for the planet. We can say that the amount of radiation that Earth receives from the sun has to equal the amount of radiation that it emits. Otherwise, it would get more and more radiation. It would get hotter and hotter and hotter, and it would change in temperature. But we know that the Earth is relatively steady in temperature. It's not significantly warming up to become the temperature of a star, or as it gets more and more radiation from the sun. It's removing that radiation by emitting its own light. So, using this knowledge and the fact that the amount of radiation that the Earth receives must equal the amount of radiation that it emits, we can calculate what the temperature of a planet is, or in this case, the temperature of the Earth. And I've reproduced the equation for this right here. So, the temperature of a planet, the equilibrium temperature of the planet, in which everything is balanced in equilibrium, is equal to the temperature of the star. So that kind of makes sense. The hotter the star, the hotter the planet will be, times the square root of the size of the star. So the bigger the star, the more light it can emit because it's got a bigger surface to emit that light through. So therefore, the more light you can give off, and therefore the hotter your planet will be, divided by the distance from the planet to the star. So the farther you are away from the star, the cooler your planet will be. That also makes sense to us. Times this correction factor, which accounts for the reflectiveness of the planet. So, why does the reflectiveness of the planet come in? It turns out that the more reflective a planet is, the less the light from the star actually makes an impact. If all of that light from the sun bounces off our planet without really doing anything, then our planet stays cooler. And we can notice the same phenomenon here on Earth if you've ever gotten into a car on a hot day. So here are two different cars. They're the same model of car. One of them is black and one of them is white. And this fellow here is looking at them with an infrared camera, which tells how much of their own black body light that they're giving off, and therefore can tell you their temperature. And what he found is that this white car is significantly cooler than this black car. You can see here this black car in the infrared, in the wavelengths where its black body emits, seems to be giving off more radiation because it's hotter than this white car does. So you can see that there are more white tones on this dark car than there are in this white car. So the more reflective a car and or planet are, the cooler they will be. So if we go back to this equation and we plug in values for Earth, so knowing the temperature of the sun, the size of the sun, how far Earth is away from the sun, and how reflective the Earth is, we can plug those into that equation and calculate that the equilibrium temperature of Earth is about 255 Kelvin. And it turns out that that is about -1 degree Fahrenheit. That's pretty cold, even for Wisconsin. The average temperature over the entire Earth should be -1 degrees Fahrenheit. But that's not actually what we measure. Earth's average surface temperature is about 288 Kelvin, or about 59 degrees Fahrenheit. So, a much more pleasant temperature for us to live. So that begs the question, why is there this difference between our naive guess as to what the temperature of Earth should be and what it actually turns out to be? And the answer has to do with the fact that Earth's atmosphere is transparent to visible light, but it is more opaque to infrared light. So in this graph here, I'm showing the atmospheric opacity on the y-axis, basically how opaque, how much light is blocked by the atmosphere at many different wavelengths. So you can see here that our atmosphere blocks basically all light at very short wavelengths. So ultraviolet light, X-rays, gamma rays, all of this is blocked by our atmosphere. That's a good thing. That means that we're protected from those high energy rays from the sun, from other cosmic sources that might give us cancer. And unfortunately, we're not quite blocked from the ultraviolet rays that will give us sunburns. So you still need to wear your sunscreen, even though our atmosphere does a really good job of protecting us otherwise. There's this convenient hole where we can see a lot of light coming through invisible light, where our eyes operate. This is also very useful. It means that we can see things with our eyes. It means that we can, navigate our world effectively and not have to worry about looking through large amounts of atmosphere that's opaque, even though we're in the atmosphere. And then in the infrared, it becomes a little bit more opaque again. And then it becomes very opaque in the far infrared to the radio. Then there's a window over here where you can let radio waves pass through. This is, again, very useful for us because that means we can use these radio bands to communicate with each other. And then further along into longer wavelengths, it becomes opaque again. So Earth's atmosphere is fairly different in where in how much light it allows through as a function of wavelength. And it turns out that this property is the reason that our planet is warm. So the reason for this is because when sunlight shines onto our Earth, mostly that sunlight is emitted in the visible range. So here I'm showing several different black body curves again. And on the y-axis is the brightness of the source, and on the x-axis is the wavelength of light. So this yellow curve here that's labeled 5777, this is approximately what the spectrum of the sun looks like. You can see here that the peak, most of the light, is coming out right around the visible range in our spectrum. So wavelengths between about 400 and 700 nanometers. You can see this prism here showing the colors of the rainbow as we perceive them. But if you have a cooler planet, say something with a temperature around 300 Kelvin, like our own Earth, it's going to emit most of its radiation in the infrared, where our atmosphere is less transparent than it is in the visible. So, what that effectively does is it allows the sun's radiation, these orange rays here that I've drawn, to pass through the atmosphere, this grayish blob I'm using almost like a blanket. This is, of course, a bit of a cartoon. The atmosphere, of course, extends all the way down to the surface of the planet and isn't just one thin layer, but you can think of it like this. So, all of the light from the sun effectively goes through the atmosphere and hits the surface. Then the surface absorbs some of it. That part that it absorbs then gets re-radiated as infrared light because it's black body emission from our warm planet. But because our atmosphere is more opaque to this infrared light, some of it hits the atmosphere and is reflected back down. And that extra heat, this extra blanketing effect by our atmosphere, warms our planet up. This is called the greenhouse effect. And the reason it's called the greenhouse effect is because this is how greenhouses work. They do the exact same thing. Glass windows allow visible light to go through, but glass is opaque to infrared light. So when you have a greenhouse, even when it's on a cold day, as long as there's sun, you can trap some of the heat from the sun into here, and it's not allowed to escape out the glass windows. So the greenhouse will be warmer than the surrounding area. The greenhouse effect is a good thing. This is the reason why our planet is habitable. I don't know about you, but I don't think I would be happy living on a planet where the average temperature is -1 degree Fahrenheit. I think often it's cold enough as is here in Wisconsin. So this is a good thing. It helps our planet be habitable. It helps our planet have liquid water, and it helps life exist. So I'm going to dive in next to what it is that makes the atmosphere more opaque in the infrared. And the answer is spectral lines. So we've talked about spectral lines throughout this class. These are the fingerprints of the elements. And in the infrared, it turns out that there are lots of fingerprints of molecules. And these are typically seen as water molecules. So here we can see on this plot the fraction of light that's allowed to pass through the atmosphere as a function of wavelength in the infrared. So the visible light is down here near the very short wavelength side. All of this is the infrared here. And you can see in this graph that there are these big spectral features, so these big regions where a lot of light is blocked. And the molecules that contribute to this blockage are shown here as labels. So there's a lot of blockage due to spectral features from water. Water absorbs infrared light and radiates it back down. Carbon dioxide, here's a couple big ones. Here's a really big one for carbon dioxide out at about 15 micron wavelengths. Here's another water, here's a methane, here's a big ozone band. So all of these molecules contribute to infrared light having a harder time escaping our planet than it did coming in as light in the visible band, because the visible band is much more transparent than the infrared band. If you have more of these molecules in the atmosphere, it only makes sense that they will block more light. So you can think of it as almost stretching these spectral features down so that the total transparency decreases on average over this entire region. I'll show you that comparison again. Here you add more of these spectral, more of these molecules, and increase the importance of these spectral features. Okay, so now that we've covered the theory of how this works, let's take a look at some data. And the data that is the most important in terms of seeing the effect of this is the trend over the last century or so that the average temperature of the Earth is increasing. So you can see this here. These are average annual means. There are variations year to year in the temperature of our Earth, but there's also a clear, unmistakable trend upwards that over the last century or so, the average temperature of our planet has gotten warmer by about 1 degree Celsius. And it's clearly larger than any of the variations year to year. And it turns out that Though the variation that we see is not necessarily larger than the variations that happen on historic timescales. This is a plot of the temperature of the Earth on average over the last 10,000 years or so. And you can see that there are these big variations. The change in the last century is different because it's much faster. You can see this change in the last century here. It's this almost straight upward shot. So, what could be causing this? Well, it turns out that meanwhile, the concentration of greenhouse gases in our atmosphere are also increasing. So here's a plot of the amount of carbon dioxide in the atmosphere as a function of time. So starting in the 1950s, we've measured an increase in carbon dioxide in the atmosphere from about 320 parts per million to about 415 parts per million. So over the last 60 years or so, the amount of carbon dioxide in Earth's atmosphere has increased by about a third. So that's a fairly big increase. You can look at this on a historical time scale as well, over the course of the last 100,000 years or so. The way you make these measurements is you go to Antarctica and you drill deep cores in the ice. So you go down many, many layers of ice that was formed many, many years ago. And in those ice are little air pockets, and you can measure the concentration of carbon dioxide in each of those little air pockets as a function of how deep that ice came from. And that tells you how much carbon dioxide there was in the atmosphere all the way back to the very beginning of the ice sheet that you were able to dig. So you can get these very long records of how much carbon dioxide was in the atmosphere all the way back using this technique. And again, you can see that carbon dioxide does fluctuate in Earth's atmosphere naturally over the course of, tens of thousands of years. But again, there's this very rapid spike in the last 100 years or so, which has brought the level of carbon dioxide in the atmosphere up from about 300 parts per million to about 400 parts per million relatively rapidly. So if we look at an intermediate time scale, we can see that this rise in carbon dioxide in the atmosphere started happening in about the 1700s to 1800s. And perhaps importantly, this is about the time of the Industrial Revolution, when humans began burning large amounts of hydrocarbons in order to power our devices and to power our industry. This is the Industrial Revolution. And since the Industrial Revolution began, we've been burning increasingly large amounts of hydrocarbons like coal and oil and gas that, as a byproduct of that combustion process, release carbon dioxide into the atmosphere. So it's possible that this increase in carbon dioxide is a result of the burning of hydrocarbons that began in the Industrial Revolution. So looking at correlations like this, it's highly suggestive that there's some link between the very rapid increase in temperature that we've seen on our Earth and the very rapid increase in carbon dioxide concentration and the timing of that carbon dioxide concentration increase happening along when we started burning large amounts of hydrocarbons and releasing carbon dioxide into our atmosphere. So it's very tempting to say that this is due to human interference. But Earth's climate is a complex system, so we need to be really careful when we start making causal statements like that. And the best way to make statements like this and to be confident in them is to model the entire system. One of the ways that we can do this is with something called a general circulation model. So the way this works is you divide up the Earth into a grid. That's a grid both on the surface of the Earth that has the simulated oceans, that has simulated land mass, simulated plant mass, and also in the atmosphere. And you can grid the atmosphere and go higher and higher into the atmosphere. And basically what you do is you study how all of the air interacts and how all of the air moves around the Earth and what the climate will do. These are the state of the art for understanding the processes in our climate and how they relate with processes going on in our oceans and processes going on in our forests. And the thing that's really nice about these general circulation models is that once you get it going, you can start turning on and off different components, and you can start to understand causal relationships. Why are we seeing these changes in temperature? Why are we seeing these changes in carbon dioxide? It turns out that these climate models, especially the GCMs, can very accurately describe and predict Earth's climate. Here is a plot showing both real data, so these colored lines here are real data, and these gray lines here are climate models that are both post-predicting, trying to match observations that already had taken place, and also predicting what the temperature of Earth is going to do in the coming decades. And it turns out that these climate models are actually pretty good at predicting how the Earth's temperature is going to change. Even in the 1970s and 1980s, they were getting the trends right. And by the mid 2000s, they're really nailing the exact amount of temperature change, the exact amount of warming that we see in our climate. So it turns out that these climate models can accurately describe Earth's climate, and more importantly, they can actually predict it. It's one thing to build a model that describes all of the observations that you have at hand, but it's a totally different thing and a much stronger statement if you can build a model that predicts what things are going to do in the future. If you can do that, then you're really sure that you can be onto something, and you can be really sure that you have a good understanding of the physics of what's happening. And based on these global circulation models and these climate models, we can now do experiments to see just what could be causing this increase in temperature and this increase in carbon dioxide that we've seen over the last 100 years or so. And the answer is that it has to be related to humans. So here's the money plot that shows this. So on the y-axis here, we're showing the temperature of Earth, both in measurements, these black line here. So these are the global averages of temperature. And you can see that there are year-to-year fluctuations, but you don't want to look too much at the fluctuations. You want to look at the trends. And these orange lines and these red lines are different models and different model runs. And you can see that on average, the model is doing a really good job of predicting the trends. And it even is able to predict dips in the temperature when or other events take place, such as volcanic eruptions. So the top panel here is showing a model that includes both natural changes to the climate, natural forcings, it says, and also human-caused ones, anthropogenic changes. And this model that includes both human causes and natural causes to changes in our climate does a really good job at predicting how our temperatures are changing over time. But when you only include natural causes, when you only include natural things like changing the amount of aerosols in the atmosphere due to volcanoes, you can't predict the rapid temperature rise that we've seen over the last couple of decades. You really have to have human causes in your models in order to correctly describe the data. This is really good evidence that what is happening in our climate, what is changing the temperature of our planet, is due to human activity. Because with these global circulation models, we can turn on and turn off different aspects, and we don't have to worry too much about what the causation is, because we can just directly check in both cases whether these things are caused by humans or whether they're caused by something else, and we're only here observing them. So to summarize, the evidence that we have is that there is an increase in temperature and an increase in carbon dioxide fraction in Earth's atmosphere. These increases are taking place at the same time, and both increases are happening much more rapidly than previous changes to Earth's atmosphere, even though the total change that we've seen in the last 100 years or so is not huge compared to what has happened over the long term on Earth. We have a plausible explanation for why an increase in gases in the atmosphere, such as carbon dioxide, could be taking place, which is that over the last couple of 100 years, we've increased our industrial emissions. We've started burning more and more fossil fuels, burning more and more hydrocarbons that release carbon dioxide into the atmosphere. We have a physical mechanism, the greenhouse effect, that relates the two phenomena and pretty simply explains why more carbon dioxide in the atmosphere means that the planet would get warmer. And it turns out that the amount of carbon dioxide and other greenhouse gases that we've added to the atmosphere matches the amount of warming that we've seen. We have a way to model the entire climate system that both reproduces historic data and also predicts the climate into future decades accurately. So we have a good understanding of what important processes take place in our climate. And the proof of that is that we can predict it and we can model it well going back in time and going forward in time. And finally, if you take those models and you turn off industrial emissions in those models, we can no longer successfully reproduce or predict Earth's climate. You have to have that in the model in order to predict what we see. So all of this put together gives us two options. Option number one is that we're very unlucky and that there's a large series of coincidences that are conspiring to make us think that something is going on when really we're just looking at natural changes. So in order for this to be true, you would need to have the measured increase in temperature not be caused by the increase in carbon dioxide. That's plausible. We would need to be living in a time with unusually sudden changes in both temperature and carbon dioxide compared to the geologic record going back hundreds of thousands of years. That's a little bit less plausible, but we can give the benefit of the doubt. Our climate models have to be missing some physics that explains the increase in temperature in a way other than industrial emissions. That's of course plausible. And we just happen to be lucky that our models correctly predict the continuing increase in temperature despite missing this physics. Again, plausible, but not particularly likely. This scenario requires a lot of things to go wrong for us, and it requires a lot of different, relatively unlikely things to be true. The far simpler and more accepted explanation is that humans, and in particular our industrial emissions, are driving an increase in the planet's surface temperature and therefore increasing the greenhouse effects. And this is why our planet seems to be getting warmer. So in this class, we've talked about a lot of different scientific debates. And we've talked about how long it takes for scientific consensus to be made. And even in some cases, like in the case of the Big Bang Theory, where almost everyone in the field feels that, the Big Bang is a very likely, way to explain the beginning of our universe, there are still some dissenters. This is the same situation here. There's very clear evidence that humans are driving an increase in the planet's surface temperature. It's possible that we're wrong, very unlikely, but possible. But this general consensus and the general wisdom is that this is what's going on. So the best way to move forward here is to take this as the very, very likely truth and to plan our actions going forward, assuming that it is true. So the way to move forward here is to think about this in the same way as the Big Bang, to think, while there may still technically be some doubts, the overwhelming preponderance of the evidence points towards humans driving an increase in our planet's surface temperature. So we should move forward under that assumption. Will there be changes to our understanding? Of course. Our theories are never going to be totally complete, but that doesn't mean that this isn't right. And it doesn't mean that this isn't something that we should start thinking about now, and in something that we should start trying to solve, because there are dire consequences coming down the road. So let's talk a little bit about, based on these climate models and based on our understanding of what's going on today, where could things go in the future? We've shown that the climate models tend to do a really good job predicting how the climate is going to change decades into the future. So let's take a look at the latest and greatest climate models, the ones that include the most physics, the most different effects, and the ones that are most able to predict and match the data from previous years. And let's extrapolate these into the future and hope that they will be similarly predictive as the ones that we saw in the last couple of decades predicting today's climate. So here's a plot showing how the temperature of our planet might increase in the coming years in different scenarios. So, because this is the future, we don't know exactly what humans are going to do. We have choices. We have the ability to take measures to make this change either for better or for worse. So, this plot is showing two different scenarios. In the red, it's showing a pessimistic scenario, in which case we don't really take any action to change the amount of greenhouse gases that we're emitting into the atmosphere. And we actually get a little bit worse than the trajectory we're on right now. We increase the amount of gases that we're introducing into the atmosphere. In this scenario, starting about 2020, which is where we are today, we start rapidly rising in temperature compared to where we are. So all of the change in the last century or so has been about 1 degree Celsius. But the next century, things could really start accelerating. The typical prediction for this pessimistic scenario shows a 4 degree increase. So we could triple the amount of change that we've seen in the last century in the next century. But it doesn't have to be this way. We could take mitigation measures. We could take measures to start decreasing the amount of greenhouse gases that we emit. And if we do this, we can actually keep the change in temperature relatively low. So instead of gaining 3 or 4 degrees in temperature, we could gain maybe half a degree in temperature over the next century and even start to see that slightly decrease. So another consequence of global warming is that the global mean sea levels will rise. As you can see, global mean sea levels have already risen about 5 to 10 centimeters in the last couple of years. This is a relatively small amount. This is about 10 centimeters here, so only a few inches of sea level rise. But that rise is expected to continue increasing and to accelerate into the future. So in the next 50 to 100 years, we could be looking at sea level rises by several feet. This is enough to start to put low-lying areas, particular islands in the Pacific, coastal areas in the United States, like Miami, low-lying places like New Orleans, at some peril of flooding because sea levels are now rising higher than many of the building foundations in these areas. This is a little bit harder to mitigate. Even if we take aggressive mitigation right now, it will still continue to be the case that the ocean level will continue to rise, but it will rise more slowly. One of the perhaps more challenging aspects that will come with a changing climate is changing weather patterns. It's not just that every part of the world will get a few degrees, maybe 1 degree warmer on average. Some parts will get warmer, some parts will get colder. On average, they will all get warmer. And also the precipitation, the amount of rain or snowfall that places get will change drastically. So these are some complicated diagrams, so I'll talk through them quickly. So on the left side here is the scenario for the average participation change under aggressive mitigation tactics. So we significantly reduce the amount of greenhouse gases that we emit over the next century. And on the right is where we don't do this and in fact have a pessimistic scenario in which we continue increasing the amount of greenhouse gases that we emit. Areas that are shaded with these crosshatches, these slanty lines, are areas where things don't change much in either scenario. So compared to the fluctuations that we see naturally in our climate from year to year, there won't be significant changes in the amount of rainfall in all of these regions with shaded regions. So if we're able to aggressively mitigate climate change, most of the inhabited parts of the world, excluding Antarctica, the Arctic, and a little bit of Siberia, most of these places won't see significant changes in rainfall over the next century if we're able to aggressively mitigate the climate change that we're seeing. But in this diagram, you can see that if we're not able to mitigate it, there are going to be significant changes in lots of areas. There are going to be areas where you can get much, much less rainfall than normal. So Southern Africa will see significant changes towards less rainfall. The United States will see significant changes towards more rainfall in some places, and in Canada. The Amazon rainforest will see less rainfall. It will scramble our climate, and it will make it really difficult to continue food production in the way that we do, and could lead to global famines and global supply chain issues, because all of a sudden the crops that you've been building and growing in your region are no longer suited to the different temperatures and the different amounts of precipitation that you get now that the climate has changed. So this is a potentially big problem over the next century if we're not able to significantly mitigate what's going on here. But I do want to emphasize that mitigation is still possible. This scenario that I've been showing, this best case scenario, does not mean that tomorrow we have to stop emitting greenhouse gases. It's this blue line here. It's a gradual decrease. And this is something that we can do. We have the technology ready to fill in. We have the ability to produce energy through wind and solar power relatively cheaply. Wind power in particular is very mature in terms of being able to produce energy at competitive rates. We just have to invest in it, and we have to make it a priority. And if we are able to do that, we can save ourselves a lot of problems over the next couple of centuries, and honestly save ourselves a lot of money in the next couple of centuries, as we avoid having to build dikes to keep Miami from flooding. And we have to avoid, building new supply chains and converting all of the crops that we've grown in locations when they're no longer hospitable. So I wanted to finish up on a slightly lighter note and tie this back a little bit more to the typical part of this course, which is that if we don't manage to succeed in changing our emission practices, this industrial pollution that we put into our atmosphere could actually be seen as a technosignature to alien astronomers. If they are able to measure the composition of our atmosphere, they could see that there are chemicals in our atmosphere that are not necessarily expected to be there without some sort of advanced technological life. And I thought I would show this press release because it has a couple of entertaining quotes. The first one is, "We consider industrial pollution a sign of intelligent life, but perhaps civilizations more advanced with us will consider pollution a sign of unintelligent life, since it's not smart to contaminate your own air." And also, people often refer to extraterrestrials as little green men, but the extraterrestrial is detectable by this method being looking for pollution in their atmospheres, should not be labeled green because they're environmentally unfriendly.